So you're not, you might be not even able to see from here. No? Okay. You can see? Okay. All right. So we're doing more with inverses today. And I'm adding to the notes because what we have here isn't exactly what you're going to see on Delta Math. So I have a few extra things to talk about. So today we're going to be verifying inverses. Really, we're just working with inverses more today. I am going to show you how to prove functions are inverses. It's kind of a neat thing, but ultimately, you know, once you see it and you're like, oh, okay, we're never going to do it again, okay? But we are going to be working with inverses some more today. So, verifying inverses. Two functions are inverses if they are reflections of each other. If they are reflections of each other in the line y equals x. So two functions are inverses if they are reflections of one another across the line y equals x, which is what we're doing when we're solving for inverses. So let's see how this works. We want to find the inverse of each function, and then we're going to verify graphically what that looks like. We're going to do a little bit more of that too. But here, we want to find the inverse. How did we find the inverse yesterday? Switch the x and y. Swap and solve. So swap and solve. So this says y equals 3x minus 6. We're going to change it. Swap your x and y. So x equals 3y minus 6. And then I need to do what to solve for y? Add 6. So we get x plus 6 equals 3y. And then divide everything. Excuse me. Divide everything by 3. So we get y equals, but I'm going to change it to f inverse of x equals, here we have x plus 6 over 3. I'm going to clean that up a little bit, just x over 3. I'm going to write 1/3 x. Can I write 1/3 x instead of x over 3? Is it the same thing? Yeah. Plus 2. Okay, I'm writing it in this form simply because it's easier for me to graph. So I'm going to graph my original function here, 3x minus 6. We're going to graph that. I'm going to graph that in pink. 1, 2, 3, 4, 5, 6. So starting at negative 6, and then what's the slope of that pink line? 3 over 1. So my slope is 3 over 1. So up 3, 1, 2, 3, right 1. Up 2, 3, right 1. Ugh, her graphs are so small. This is my one critique here. 1, 2, 3 over 1. So I'm graphing a lot of points just because I kind of want them. I want you to see what's happening with those points. So there's my pink line, right about there. It's pretty good. So that's F. And I'm going to go ahead and just make a little table of values because, again, I'm pointing something out here. My ordered pairs here on my pink graph were 0, negative 6. Then I had 1, negative 3. And then I had 2, 0. And my next point was 3, 3. And then my point after that was 4, 1, 2, 3, 4, 5, 6, 4, 6. Okay. So I had lots of points there on my pink curve. Okay, so now I also want to go ahead then, and I'm also going to graph my inverse function and just see what this looks like. So my inverse function starts at 2, and then, yeah, the slope is 1/3, so that's going to go up 1 and right 3. So it's going to go up 1 and right 3. Oh, look at that. And then up 1 and right 3. And up 1 and right 3. I'm going to do it in reverse too, just a second. I'm going to go down 1 and left 3. So I get another point there. Okay, so there's my blue graph. If I did it one more time, then I'm going to go down 1, 1, 2, 3. Oh, and I'm right there. So interesting. Okay, so here's my blue graph, which happens to be my inverse function, so f inverse. And again, I want to look at these ordered pairs because there's some, very interesting stuff happening here. On my blue curve here, and I went in both directions so that I, again, have really good points here. My first point here, my x-intercept is -6, 0. Hey, look at that. And then I have -3, +1. And then I have 0, 2. And then I have 3, 3. And then I have 6, 4. Yeah, hey, look at that. What do you notice happened with those inverse ordered pairs? They're just swapped, right? Everything just swaps. And that's literally because we swapped the x and y, didn't we? And solved for the other guy, essentially, okay? And so what we get here is we get these ordered pairs that have swapped, and really, it is a reflection across the line y = x. So y = x is that diagonal that goes through 1, 1, 2, 2, 3, 3, 4, 4. It's our perfect diagonal on the 45, right? This is the line y = x. And what happens is a reflection takes the point and it reflects it perfectly across that line y = x. And by perfectly, I mean perpendicular to, okay? And that's what a reflection is. It goes perpendicular across that line of reflection, which is kind of a cool thing. Now that you know that, so yes, they are reflections of one another across the line y = x. We can kind of see that pretty clearly, okay? All those points just get reflected perpendicular across that beautiful purple line there. So, now, how do we use this information? And this is what I want to talk about today. So we're going to not do this one because I just don't care. I want to do something a little bit different. So using inverses. Again, what you guys at this level need to understand is the notation, okay? So here is one problem we're going to do. I'm going to write it right here. So I want you to find f of 10 plus 2 f inverse of -6. This is an interesting question. Again, and it's just notation. And what they're going to give you here, they're giving me information. So this is our goal. This is our objective, what we have to do. And the information they're giving me is they're giving me a table of values for my f function. And my table of values for my f function are, let's see, 7, -6, 19, 2, 10, 7, and 5, 10. So we need to figure out what they want us to do here. What do you think this means? Like, what does f of 10 mean? See, and that's what we want to understand. Does it mean f of 10, or is this function notation where it's saying f of x, and what are we putting in place of x? The 10, okay? And so it's really saying, hey, if x is 10, what is the value of the function? What is the output? If the input is 10, what is the output of our f function? Is it, if we look at our ordered pair here? What is f at? It's 7. Yeah? Okay. So this says, hey, go to your f function. If the x value is 10, what's the output? The output is 7, right? Okay. Now what is this one over here saying? Times 2, yeah. So this is a times by 2, good. But what function do we need to know? Inverse, yeah. This is saying, hey, using the inverse function, do I have the inverse function? Can I create the inverse function? Yes, I can. If I have a table of values, then I can also create my inverse function pretty easily. Yeah, well. Say that one more time. -6, 7. All we have to do is swap those things. Just trade places. We're Eddie Murphy here. Trading places. Anybody? Anybody? Okay. All right, I'll show my age. Okay, and then 19.2 becomes 2.19, and 10.7 becomes 7.10, and 5.10 becomes 10.5. Okay, so we can, if we have a function, we can do the inverse pretty easily, right? Now we can figure out what it wants here. F of 10 is 7. F of 10 is 7, plus we want 2 times F inverse of negative 6. What does that mean?
Wait.
7.
It's 7. Yeah, so this is saying go to your inverse function, and if the input is negative 6, so here's our input of negative 6, and what's the output? 6, 7. Okay. All right, so F inverse at negative 6 has a value of 7, and now it just needs us to do a little bit of math here. 7 plus 14 gives us 21, okay? So this is all about understanding notation. Now I have another one for you. That was number 1. Here's number 2. Number 2 says, hey, find F of F inverse of 7. F of F inverse of 7. This is a composition of functions. It's a function within a function. A turducken, if you will.
What? I want to eat a turducken.
Do we not know what a turducken is? Oh my God, you guys!
Why? What is it?
It's a turkey with a duck stuffed inside, with a chicken stuffed inside of that. A chicken inside a duck inside a turkey. It's a turducken.
How do you cook that?
For a long time. All right. Okay, so we got to start from the inside out. This is what we were doing the other day. So we're going to start with the inside of this function, which is saying for us to do what?
Find the inverse of 7.
If we have it, using our inverse function, you look at we got our table already. We're referencing the same info here. So the input is 7. What's the output? No. So this is saying if your input is 7, the out, yeah, so we're finding, so that is 10, and so that's the inside piece, and now we want, hey, now we can move beyond that and say, now it says using the F function, what's our input now?
7.
Oh, that's the output, yes. We're going back to 10, the output is 7, and that's our answer, okay? Wow, look at that. The function, look what happened there. What happens when you have a function composed with its inverse? It goes back, they're inverses. They undo one another. They cancel each other out. That's what inverses do. Okay, interesting, yeah? Okay, so that's what inverses do. They undo the thing. They undo one another, all right? So now let's verify inverses, because this is where we prove things algebraically. To verify inverses, all we have to do is compose them. So, two functions, f and g, two functions f and g are inverses if f of g of x equals x. F of g of x equals x, and g of f of x equals x. They should, if they're inverses, they should cancel each other out, and the only thing we're left with is x. All right? So we're going to do that so you can see how it works down here with 3 and 4. So I want to prove this, and you're going to see how this is kind of interesting. We're going to start with f of g of x. F of g of x. And again, I want to go through the math here. We're going to start on the inside. What can I replace g of x with? 2x plus 7. So I have f of 2x plus 7. Okay. Now, what does f of 2x plus 7 tell me to do? plug that in for x. So replace the x with the 2x plus 7. So I'm going to go to my f function and say, hey, instead of the x, I have 2x plus 7 on top, then minus the 7, all divided by 2. So let's clean this up. What do we clean up first? Yeah, positive 7 and negative 7 cancels out. So I'm left with 2x over 2. And what is 2x over 2? It's just x, yeah. So hey, look at that. F of g of x, everything cancels out in kind of a cool way, and we're just left with x. All right, that's half of your proof. So now we got to do the other way. So now we want g of f of x. So now we can sort of reverse. What can we replace f of x with? So now we have g of x minus 7 over 2. All right, what's g of x minus 7 over 2 tell me to do? Plug it into that x over there. So instead of the x, we're using the pink stuff there. So it'd be 2 times a big old x minus 7 over 2. And then the plus 7. See what I did there? So instead of the x, we're replacing the x with our big old quotient there. All right, so now we clean her up. What cancels out when we do times by 2 and the times by 2 and divide by 2 would cancel each other out. And so we're left with the x minus 7 plus 7. And what happens there? You just get the x because the positive 7 and negative 7 make a 0. All right. So this is a proof that they're inverses. When you compose them, everything cancels out in a nice logical way. So if you were to solve it, you could pretty much, subtract the 7 and divide by the 2. Really easy to do, right? This is how you prove it. Now, again, it's kind of cool, but that's all we're going to do with it. All right? You've seen it once. Maybe you'll remember that, don't you compose the functions, like you put f of g of x and g of f of x, and they come out to just x, like, maybe you'll remember. So, here's what we're really doing today. So that's kind of a cool thing about inverses. That's really sort of what they do. So, a couple more examples today of some finding inverses that are a little more complicated. We're going to do this one here. And 7, and then this, and I have one more below, but okay. We want to find the inverse of each function, but I'm not gonna do all the rest here. It's a complicated function here, and I want to find the inverse. What do we need to do to find the inverse? Yeah, swap and solve, ladies and gentlemen. So instead of y equals x equals y over 5 plus 2y. Okay. Lots of y's going on here. What's the first step we should do? Yeah, this is like x over 1. So we are going to multiply, cross multiply, if you will. So this is going to be x times 5 plus 2y equals 1 times y, or just y. Cross multiply. Now what do you want to do? Craziness, right? Like, what do? There's multiple y's. Distribute. So we can't divide by x, because if I divide by x, I still have this weirdness here. We actually do need to distribute on this one.
5x plus 2xy.
Equals y. So we're going to distribute 5x plus 2xy equals y. Now, what we need to do is we need to collect the y's. They need to be on the same side. So I need to take this term and move it over here with his friend, because I need all the y's. Subtract 2xy to the other side. So I have 5x equals y minus 2xy. GCF, very good, right here, greatest common factor. They have a y in common, so we need to undistribute that y. So if we take out the y, what's left behind? 1 minus 2x. Excellent. And now how do you get the y by itself? Yeah, we can divide both sides by the 1 minus 2x bubble. So that whole bubble can disappear to the other side. And so we get y equals, but I'm going to switch it around because it's the inverse function now. Well, f inverse of x equals 5x over 1 minus 2x. Okay, you good with that? That's a lot of math. It's a lot. That is the answer. It's a lot of math. Knowing how to do this will be so helpful. So we're going to do one more for practice here. So here I have another. F of x equals 3x plus 1 over 8 plus 5x, sorry. Swap and solve. So we're going to swap our y, becomes an x, and that x has become y. So 3y plus 1 over 8 plus 5y. X over 1, and then we're going to cross multiply. Very good. So my denominator gets multiplied to the x, and the 1 gets multiplied to the numerator. So this becomes x times the denominator equals 1 times the numerator. And then, yeah, and then we need to distribute. Yeah, we're going to distribute. All right, so we get 8x plus 5xy equals 3y plus 1. Good. And so what do we need to do? Get the y's on the same side. So you want to, yeah, okay. So we can subtract 1, so that moves over to the left-hand side. We can also subtract 5xy. So it moves over to the right-hand side. All right, so I have 8x minus 1 equals 3y minus 5xy. When I look at the right-hand side, they have something in common. Greatest common factor. Greatest common factor. So they have y's in common. We're going to take out that y. Good, 3 minus 5x. Yeah. And then to get the y by itself, we're going to divide by our 3 minus 5x bubble. Lots of math there. So f inverse of my x, which is really the same thing as the y, is going to be 8x minus 1 over 3 minus 5x. Lots of math here. This is really good math.
Do you have to graph it?
We are not going to graph it. Yeah. You have dozens. We're going to do just one more here on number 7. I just want to talk about number 7 really quick. Do you have any questions on these two rational ones? Rational fractional ones? Again, it's a process. Once you learn it, it's actually pretty easy. But this process comes up multiple times in calculus, so it's good to know how to do it well. All right, so I want to look at number 7 really fast because I want to talk about the domain. And so this is the last one we're going to do. First of all, what shape is this number 7? Parabola. Yeah, it's the squaring function. It's a parabola. It's been shifted. How has that parabola been shifted? Left 4, down 2. Excellent. So it's been shifted from 0, 0. It went 1, 2, 3, 4 to the left and down 2. So here is its vertex. Its minimum value is right there, and it'd be a parabola up from there. But they have a condition here. What's that condition saying? Yeah, x only is allowed to be greater than or equal to -4. So that, from this point, is everything that would be on the right side of that. And so it's not including half of our curve to the left. So we don't want that left-hand side. And that's really important because if we didn't have this domain restriction, is this function one-to-one? No, it's not. It fails that horizontal line test. So we can't find the inverse of it. But because we've restricted it, we can say, hey, okay, we're good now. We can't, good now, see what I did there? Okay, so now we can find the inverse of this function. All right, whatever I can do to make math funny, right? Okay, so just like before, we're going to swap and solve. So now I'm going to have x equals y plus 4 quantity squared minus 2. Add the 2, so we get x plus 2 equals y plus 4 quantity squared, and then square root both sides. All right, we're going to square root both sides. Now, normally, when we take a square root, what do we have to remember? Plus or minus. Normally we have to remember plus or minus because there are two sides to this curve. But I don't have two sides to this curve. I only have one side. So we don't actually have to worry about it, which is kind of nice. All right, so we have the square root of x plus 2. I cannot clean that up. There's a plus in there. You cannot simplify a square root with a plus in it most of the time. Subtract 4. So we get the square root of x plus 2 subtract 4, and that's on the outside of our square root, so be a little bit careful there. So now let's think about this curve a little bit. Okay. What shape is this curve?
It's like a square root.
Square root swoop. Yeah, it's a swoop. All right. And how has it been shifted? Left 2 and down 4. So we have a left 2, down 1, 2, 3, 4. Right here is where that square root swoop starts, and that's what it looks like right there. What's the domain of this inverse function? Yeah, x is greater than or equal to -2. All right, and that we can clearly see just by knowing what the shape of our graph is here. And I would like you to pay attention to how is this x is greater than or equal to -2 related to our inside function there?
2 minus 4.
No, but just ignoring that. Like, do you see there's like a x plus 2, and then this is just, it's like the opposite, yeah? Yeah, okay. We'll talk. Well, just looking here at my curve, because we know how that square root swoop shifts, we only see this curve for x values greater than -2, yeah? So I'm just looking at the graph and what we know of the graph. But yeah, we will probably get into how you actually figure out the domain of more complicated functions. But all right, very good, ladies and gentlemen. We only have this positive half of this. The other one we excluded when we limited the domain of this left-hand side. So we don't see the whole thing because it's not there. We only wanted the positive side. That's why we got to get rid of the minus part, okay? If it was negative, that'd show the bottom half of this curve, which is interesting. Anywho, we'll talk more about that later. All right, I think you can do it. The delta mass. And it will require paper. Okay.